Here we are, Mount St. Helens, in the crater. This is the Mount St. Helens SNIF site. This is a gas monitoring site that was put in at the end of August 2014, and its purpose is to monitor gas plumes within Mount St. Helens. This plume here contains mostly water vapor, but it also contains carbon dioxide, sulfur dioxide, and a really trace amount of hydrogen sulfide. And its composition is consistent with a very shallow, hot, oxidized melt. And so it's a magmatic gas, essentially, that's being emitted to the atmosphere. And has a very low carbon-sulfur ratio, which is consistent with low pressure degassing. And it also has it's mainly sulfur dioxide, very little hydrogen sulfide, which is also consistent with high temperature, low pressure degassing. This is the only place in the Cascades where we presently get sulfur dioxide degassing. Everywhere else, there's hydrothermal systems that are in between the point where the gas separates from the magma and then makes its way to the surface. It interacts with hydrothermal fluids and rocks and water, and during that process, any sulfur dioxide that's degassed gets converted into hydrogen sulfide and other species. So it's not actually emitted to the atmosphere. And so this station, which you can see in front of you, is actually a station to monitor just those four gases: water vapor, carbon dioxide, sulfur dioxide, and hydrogen sulfide. Looking at the exterior of the site, this is the north side. On the south side here, we have solar panels to power the site. Then we have a mast over here that consists of on the far right, the black thing is an ultrasonic anemometer for wind speed and direction. There's a white radiation shield, which has a temperature and relative humidity sensor for ambient air temperature and relative humidity. And then there's a box with an inlet, which that serves as the inlet for the gases. And so there's pumps inside that actively pull plume gas through a tube into the instrument inside. I'll open it up now. So inside of the station is the gas instrument, which is a self-made instrument combining several different sensors with the purpose of monitoring water, CO2, sulfur dioxide, and hydrogen sulfide. And that's in this box right here. And it also contains an array of other diagnostic sensors, so we can tell how well the station is working, tracking things like flow, are the pumps working, the temperature of the station, the pressure, all these sorts of things. And it also has an array of chemicals and small gas bottles, which allow us to do automated sensor verifications. The chemicals are used to check the baseline of the sensors, so it scrubs out water, CO2, SO2, and H2S, so we can see if there's any significant baseline shift in the sensors. And then the gas bottles contain mixtures of gas containing CO2, carbon dioxide, sulfur dioxide, and hydrogen sulfide, known concentrations, which we periodically sample automatically so that we can verify the response of the sensors. See, are they changing with time? Is there a problem with the sensors of any kind? And so in this orange box next to the gas instrument, which the gas instrument is referred to as a MultiGAS, this orange box contains additional equipment that, such as a solar charge controller, which controls the charge of the batteries. There's about 10 lead acid batteries in here, hopefully, which will help us get through the winter. And the orange box also contains a 900 megahertz radio, which provides a link back to the CVO. So we have two-way communications, so we're constantly downloading data, but we can also interact with the station in the same way as if it were plugged in on our desktop. And another measurement, sort of charismatic measurement that the station makes is it measures the temperature of a fumarole vent just over here to the south of us here to the left, which currently is about 370 degrees C, or around 700 or 750 degrees Fahrenheit. So there's actually a long cable that runs down the other side of this ridge, and you might be able to see some of that heat shimmer there above those sort of white and pink altered rocks. And this is a remnant from the dome, one of the spines that was extruded during the 2004-2008 eruption of Mount St. Helens. And presently, it's the only place we're aware of that emits sulfur dioxide in the Cascades. This is a very challenging place to make gas measurements, or to make any measurements for that matter. It's a high elevation site. We're at about 7,500 feet in the Cascade Mountains, so we receive crushing snow loads, ice, wind, rain, and to add to that mix, we also have corrosive volcanic gases. So this is a very challenging place to do business. It's a challenging place to make instrumentation run for any period of time, and it's also an even more challenging place to get good quality data. We've done this sort of work elsewhere in the world, around the equator in Southeast Asia, and colleagues have done this sort of work in Italy and other places. By improving our capabilities for continuous gas monitoring, we're better able to track activity and detect early indications of volcanic unrest. When used in combination with other monitoring data, such as seismicity and ground deformation, we can piece together a comprehensive model for what we think is going on at the volcano. In this way, we're able to provide the public, government agencies, and the media with comprehensive information regarding the present state of the volcano, as well as forecasts of volcanic activity in the event of unrest. Ultimately, these data contribute to the overall understanding of how these incredible, explosive volcanic systems work.